So now you're world experts at pentanes. What could be better than to move to hexanes? And we got 5 isomers of hexane, the C6H14. Let's first of all think about what those isomers are. We've got one isomer that has the 6 carbons in a row. Now if we take a chain of 5, there's some methyl left. That methyl can go in this position to give us 2-methyl, or it can go in this position to give us 3-methyl, and in both cases those are pentanes. Now it's the end of the 5 carbon chain ones. There's nowhere else we could put that methyl group. If I put it there, then it's just 2-methyl, and if I put it there, then it's just hexane again. So let's go to the 4 carbon chain, the butanes, which are going to have 2 carbons or 2 methyls left over. And we can have the one isomer where both of those are on carbon 2, so that's 2,2-dimethyl butane, or we can have it here for the 2,3-dimethyl butane. So 5 isomers of hexane. Let's have a look first of all at their carbons, the number of different carbons there are in there. So for the first one, I hope you'd agree that the 2 on the end are the same, the 2 next to the end are the same, and then these 2 in the middle are the same. So we got 3 peaks that we would expect from the carbon NMR of just N-hexane. Now let's move to the 2-butyl pentane, and we've got a carbon there and a carbon there that are indistinguishable. So I'm going to call those both carbon 1s. Then carbon 2, carbon 3, carbon 4, carbon 5 are all different. So therefore I would expect 5 peaks there. Moving now to the 3-methyl, and I hope you would see that this carbon on the end and this carbon on the end are the same. Then these 2 are the same, so that's 2 types of carbon, 3 types, and then this methyl 4 types. Okay. Hopefully you can start to see when carbons are going to be equivalent. One easy little thing is start counting and from one end and then try from the other end. And if they're indistinguishable counting wise, then they're probably indistinguishable chemically wise. Moving here, we got 1, 2, 3, 4 in the butane, and then these 3 methyls here. Now again, start counting. It doesn't matter if I start 1, 2, or 1, 2, or 1, 2, all the same. In other words, these 3 methyl groups should all be carbon 1, and then carbon 2 there, carbon 3, carbon 4. So 4 peaks for that one. So we now got 2 isomers that have 4 peaks in the carbon NMR. Might be tough to distinguish those, although I'm going to be very naughty when I get to that and break all kinds of rules in order to do that distinguishing. But before we do that, I do get ahead of myself. Let's look at this 5th isomer, and I hope you would agree that we've actually just got 2 types of carbon in this one. We've got the kind of carbon that's the methyl groups on the end, because again, it wouldn't matter which one of these I started counting from, it would always be 2,3-dimethyl butane, and then you've got the carbon 2 and the carbon 2 there, or carbon 2 and carbon 3, however you want to do it. Those are identical because they're both going to 2 methyl groups and to each other. So thus just 2 peaks for this particular one. So when we look at the carbon, we're expecting 1 2-peak spectrum, a 3-peak spectrum, a 5-peak spectrum, and then 2 4-peak spectra. Looking at these here, easy ones are the ones that we knew about. There's the 2-peak, so spectrum E goes with the 2,3-dimethyl butane. So then you've got the, where am I, 3 signal one. This is just the straightforward hexane, 3 signals there. And then when we get down to the 1, 2, 3, 4, 5, we can see that's the 2-methyl pentane, unambiguously determined. Now, I said I was going to be a bit naughty because when we get into proton NMR, then there is a relationship between the peak heights and the number of hydrogens that give rise to those peak heights. You are told that that is not the case for carbon NMR. And indeed, because the carbon NMR is just looking at 1% of the carbon nuclei in a sample, whereas the proton NMR is looking at 99% of the protons in a sample, it's certainly not something on which you can rely. But there you can, and I have to be very careful how I say this, if all else fails, think about it. Think about thinking about the relative peak heights. If we look at this one here, we've got 2 carbon 1s, 2 carbon 2s, 2 carbon 3s. All of these are sort of close to the same height because there's 2 carbons giving rise to each of those. Go down to this one and you can see that there is, I would say, a significant difference in the peak heights, because one of the types of carbon is only represented by 2 carbons, whereas the other one, there's 4 carbons of that type. So while I wouldn't, put any money on it, I would be fairly sure saying this is carbon 2 and this is carbon 1, because there is a significant difference in the peak heights. Going over here to C, where we got 1, 2, 3, 4, 5, I hope you would agree that there are 4 signals that are about the same height, but one signal that is very definitely higher, significantly higher. And indeed, when we look at the molecule, you've got 1, 2, 3, 4 carbons, 1 of each, but then there's 2 of carbon 1. So I would say maybe that's carbon 1. Again, a pure NMR person would say, how dare I say such things? And it's certainly not something to hang your hat on, but it's something possibly to, put your hat a little bit close to, maybe. Anyway, with that in mind, we've assigned B, C, and E because we had the 2-line, the 3-line, and the 5-line spectra. How about distinguishing between A and D? Now, A and D, you might remember, you had the either the 3-methyl pentane or you had the 2,2-dimethyl butane. Now, again, if we look at the possible pictures of these, okay, and I'm kind of cheating here. We look at spectrum A, we've got really 3 peaks that are sort of the same, although you could say that's much smaller, but look at this dominating giant peak here. Well, when you look at the formula or the structure of spectrum A, you've got 1 carbon that is represented 3 times, and the other 3 is only 1 of. So I would say there's a pretty fair chance that that represents the 3 carbon ones. Now we get down to spectrum D, you can see that we've got 2 kind of bigger peaks and 2 smaller peaks. Well, when we look at the possibilities for 3-methyl pentane, you've got 2 carbon 1s, 2 carbon 2s, a carbon 3, and a carbon 4. So I wouldn't look at this and I would say immediately, oh, it's 3-methyl pentane. But knowing that I had to somehow distinguish between this molecule and this molecule over these 2 spectra, I would say this spectrum is much more likely to belong to the molecule that's got a distinct imbalance of the numbers of carbons, 3 carbon 1s to 1 to 1 to 1, and this one would go to one that's a little bit more representative, 2 carbon 1s, 2 carbon 2s, carbon 3, and a carbon 4. As I say, do not kind of go up and have a bet with an NMR spectroscopist about that, but when all other things are equal, you can get some teeny little inference from the peak heights.